Okay, now let's pick up again with one particular type of isomorphism, which is called an automorphism. Okay. Now, auto means self. Automobile means it moves by itself. So automorphism is self, and morphism means form. So an automorphism is an isomorphism of a space with itself. Now you might think that automorphism, that of course a space has the same structure as itself. But the interesting thing about automorphism is that the mapping of a space to itself can have many different forms. So let's look at some examples. Here's one example, a dilation map, ds. Okay. In this case, we're taking a dilation map from R2 to R2. It's possible to take dilation maps between Rn to Rn. But the dilation map always multiplies vectors by a non-zero scalar s. All right, here's a picture. Here's my picture of R2, and here's two typical vectors in R2. If I take the case where s equals 1.5, and I consider the dilation map d1.5, what that's going to do is map every vector into a vector that's 1.5 times as long. Okay, so you can see that d1.5 of v is 1.5 times as long as v. d1.5 of u is this 1.5 times as long as u. If I had a vector down here, right, then I would map it to another vector down here, which is the same direction, but 1.5 times as long. Okay. All right, now, intuitively, you would think that the vectors in this original space behave pretty much the same as the vectors in this space. You're just multiplying by 1.5. You could almost say it's like a change of units. It's like changing from inches to, from feet to inches if I multiplied by 12. Okay? So in fact, you expect the vectors to work the same way, and they do. And it's an exercise to show that this is in fact an isomorphism. Another example is rotation or turning map. I can take every vector in R2 and rotate it by pi over 6. And in that case, it will give me another vector in the same plane. This is almost like doing your calculations and diagrams on a piece of paper, and then just taking that piece of paper and rotating the whole thing by pi over 6. All your calculations and vector sums and so on will look the same. You've just rotated the piece of paper. Okay? And again, this is an exercise to show that this mapping that maps vectors in R2 to vectors in R2 is in fact an isomorphism. I'll just draw one more vector here. If I had a vector like this, like if it was going straight up here along the axis, then the result would be here, rotated pi over 6. Okay, and any vector in R2 would have a similar rotated image under this mapping t pi over 6. Of course, pi over 6 was one particular choice. You could do t theta for any of angle theta. Here's another type of automorphism. In this case, we're choosing one particular line in R2, and we're mapping vectors in R2 to their mirror image reflection under the assumption that the mirror is a long line L. Okay, so what's mirror image reflection? Well, if you think about how mirrors work, let's take the perpendicular from this vector to the mirror. And the mirror image will be the same perpendicular on the other side of L, and it will give me the vector that joins these 2 points. Okay, as you can see here. Okay, so that's how you do mirror image. If you think about it, if I took a vector along L, just took a vector along L like this, what's its mirror image reflection? Well, if you take the perpendicular from this to L, It's the vector itself, because you're already on L. So in fact, the mirror image reflection of any vector along L is the vector itself. Okay. And again, if I took some vector down here like this, if I took the vector out here, its mirror image reflection would be up here. Okay. This here again, you can check that this automorphism is in fact an isomorphism. Okay. Some general lemmas about isomorphisms. An isomorphism always maps a zero vector to a zero vector. Okay. That seems pretty clear. If you're going to have a mapping that preserves all of the structure of a vector space, you'd think that they'd have the same zeros. And we can prove that as follows. Given that F is an isomorphism, and let's use the scalar multiplication preservation property. Okay. If you consider F of the zero vector in V, we've shown as one of the vector space properties that 0 times any vector in V is equal to the zero vector. So here we're taking 0 times V in the vector space V. Okay. Now, if we use the scalar multiplication preservation property on this expression, I can pull the 0 outside of the F, and then this is a vector in W. Now we're going to use the zero multiplication property in the vector space W. 0 times any vector in W is the zero vector in W. Right? So the upshot is, look at the first and the last expression, and this is exactly what we want, that F of the zero vector in V is equal to the zero vector in W. That establishes this lemma, that zero vectors are mapped to zero vectors. All right, here's another lemma. Okay. For any map F between two vector spaces, the following statements are equivalent. First, F preserves structure. We've already talked about this. We know that isomorphisms preserve structure. So these are two conditions that are necessary conditions for an isomorphism. Note also that for an isomorphism, you also need to show that F is one-to-one and onto. But this is, these two conditions are necessary in order for F to be an isomorphism. All right, now this lemma is saying that these two conditions are equivalent to proving this single condition that F preserves linear combinations of two vectors. Okay, so that makes things a little bit easier for me. If I want to show that F is an isomorphism, then all I'll have to do is show that F is a bijection, that is one-to-one and onto, and that F preserves linear combinations. Okay, because preserving linear combinations is the same thing as showing these two statements. So I get 2 for 1. Furthermore, if F preserves linear combinations of two vectors, it will also preserve linear combinations of any finite number of vectors. These two statements are in fact equivalent. So as long as I get a function that preserves linear combination of two vectors, I get a function that preserves linear combination of arbitrary numbers of vectors. Okay. The proof is as follows. Now, if you look at these three statements, 3 implies 2 immediately. Why is that? Because 2 is a special case of 3 with n equals 2. Okay. 2 implies 1 immediately also because 1 is 2 different special cases of 2. The first special case has C1 equals C2 equals 1, and that gives me this additive statement. The second special case is C1 equals C and C2 equals 0. That will give me this second special case. So the bottom line is that the statement 2 implies the statement 1. So to show that these three, so we have this implication and we have this implication. To show their equivalent, all I need to do is show that 1 implies 3. Okay, so let's assume statement 1, and we'll prove 3 by induction on the number of some n's n. Okay, all right, this is a statement for arbitrary n, which means that it should be true for n equals 1, n equals 2, n equals 3, and so on. Now let's go step by step and show that this statement is true for any n. Okay, let's start with a base case. The base case should be n equals 1. Now when n equals 1, what is this statement? When n equals 1, the statement is f of c1 v1 is equal to c1 f of v1. That's exactly the statement here. Okay, so we're assuming 1, so we assume this is true. So statement 3, when n equals 1, follows immediately from this part. All right, so we've covered the base case when n equals 1. All right, now how does induction work? Induction works as follows. Assume this statement here for the case when n equals k. Maybe I can copy this. Let me see if I can copy this. Let's see if I can put that here so we can... it doesn't look like it's working. Sorry. Thought I might be able to get it here, but it doesn't look like it's going to work. Okay. Anyway, so let's assume that we can assume that this statement is true for n equals k. All right, why don't I just write it so you can see what that is? So we're assuming that f of c1 v1 plus ck vk is equal to f of, is equal to c1 f of v1 plus ck f of vk. All right, we're assuming that this is true. This is part of the induction. All right, and let's see if we can use this to establish the k plus 1 case. All right, to establish the k plus 1 case, let me write down the left-hand side for k plus 1. And I'll see if I can obtain the right-hand side for k plus 1. Okay, so here's the left-hand side for k plus 1. At this point, I want to use my assumption that 1 is true. Remember, we're assuming that 1 is true, so I'll write that down also. We can assume also that f of v1 plus v2 is equal to f of v1 plus f of v2. All right, so we're assuming this, we're assuming this, and we're assuming this. So I can use all of these facts to further my cause and show what I want to show. Okay. All right. So I'm going to write down this left-hand side of what I want to prove. And I can break this vector inside into two vectors. I can break it into this part plus this part. Now this is a sum of two vectors. Since it's a sum of two vectors, I can apply this assumption that comes from statement 1. Okay. So all I'm doing here is applying this statement where my first vector is this linear combination and my second vector is this single term. Okay. Now at this point, look at this expression here. Because I'm using induction, I can assume that this expression can be broken up in the linear combination way. Furthermore, look at this expression here. This expression is the same as this expression here, constant times v, so I can pull out the constant there. Okay. So actually, I can go immediately from this statement down to this statement here. Okay. And I can also go from this statement to this expression here. And that gives me the fact that inductively I can show that the statement is also true for k plus 1. Okay. I'm sure you'll have to look this over a couple of times, but the outline is very simple. You establish it for the base case. You write down your assumptions for induction. You can assume that the statement is true for k. Then write down the left-hand side for k plus 1 and see if you can use these assumptions to obtain the right-hand side of k for k plus 1. Okay. Now, this result makes it easier to check that a function preserves the structure of a vector space, since all we have to do is show that the function preserves linear combination. Remember, statement 2 simply says that f preserves linear combination. So we can do an example here. So we can take the line through the origin. All right, this is a line. Any scalar multiple of the vector 1, 2. So the vector 1, 2 looks like this. Okay. Any scalar multiple of that will look like the line up and down here. Now this certainly looks like R1, and in fact we'll show that it's isomorphic to R1. Okay. You can define an addition and a scalar multiplication on all the vectors in L. Because L is a subset of R2, the vectors in L have the same operations as the vectors in R2. Okay, and this is how it works out. All right, now we're going to define a mapping as follows. F of t and 2t, which is on L. We can also write that as f of t times 1/2. And we'll say that that's equal to t. Okay, so if I have a scalar multiple of 1, 2 here, I'm going to map that to the scalar multiple itself, which is actually an element of R1. And I want to show that this is an isomorphism. Let's first verify that f is 1 to 1. Okay. Suppose that f maps two different members of L to the same output. Well, I shouldn't say two different, just suppose it maps two elements to the same output. And we'll show that, in fact, the two must be the same. So I take f of t1 times 1, 2, and f of t2 times 1, 2. These are ways of writing arbitrary elements of L. So supposing that f of these two arbitrary elements of L are equal, but what's the definition of f? Well, f of t1 times 1, 2 is just equal to t1. And f of t2 times 1, 2 is just equal to t2. So the only way that f of this vector can be equal to f of this vector is if t1 equals t2. And if t1 equals t2, then these two elements are equal. So that means that, in fact, there's only one element of L that maps to this output. All right, next, check that f is onto. Consider any member of the codomain. And then you need to find an element of the domain that maps to it. Well, I'll just define this element, r times 1, 2. Certainly, f of r times 1, 2 maps to r. So in summary, I have a mapping that maps exactly one vector in L to every element of R1. Right. Now, to show that f is an isomorphism, we can show that f preserves structure. Here we have that f of a sum of any two vectors in L is the same as the sum of the f's. You can go through the steps here and see that that's true. Okay, actually, here he's only shown addition. What he really should show here is that we have f of some constant times this one plus some constant times this one is equal to f of C1 T1 plus C2 T2, and that's equal to C1 F plus C2 here, so that's C1 and C2 there. So really there's a deficiency here. In order to show that F preserves structure, you need to show a linear combination. So there should be a C1 here and a C2 here. Okay. And that will establish the isomorphism in one fell swoop instead of having to check addition and scalar multiplication independently. You can check a linear combination. Okay, I'm going to pause here and we'll continue.